Hello again, everyone. Welcome back to the second part of this lecture on an introduction to composite materials. In this part of the lecture, we're going to deal with that pesky detail that sometimes composites are not always formulated primarily for mechanical response, ways that anisotropy can be diminished, whilst exploring fiber-based composites a bit more. At this point, you are aware that we can create an arrangement of matrix and reinforcement across multiple length scales. Furthermore, there can be significantly different properties realized along different orientations relative to the load imposed on each region of the composite. We have seen with an example in the previous part of this lecture that the modulus in strength can vary wildly depending on the orientation of reinforcement. So too is the case for fracture toughness, which will be covered in detail in the following lecture. However, let us instead focus on what is meant by reinforcement, which has the connotations of being purely for the sake of affecting mechanical properties, and indeed that is the case for most composites, but not all. It's technically more precise to call the reinforcement part of a composite a dispersed phase. To be completely accurate, composite materials on a global basis can be described as being that which have a continuous matrix containing a dispersed phase. This is accurate in describing a relatively modern engineering composite like Al6, but also one of the first composites to be devised by the Roman Empire, circa 7500 BC, lime plaster and animal hair. Lime plaster and animal hair was used well into the last century. Lime-based plaster is still employed in grade-listed UK properties and is notoriously difficult to work with. There are many points during the application where the matrix can crack, leading to the inclusion of animal hair to bridge these cracks. The reasons for which will be covered in depth in the following lecture. However, the application of animal hair to plaster is a clear definition of dispersal. A handful or 6 of animal hair was added to the plaster during application. Therefore, expanding a bit further on what is defined as a composite, it is largely correct to describe a composite as being a matrix and a reinforcement, but calling a composite a multi-phase material comprised of a matrix and a dispersed phase applies regardless of whether the formulation is applicable to purely mechanical aspects or to other advantages. What if the dispersed phase was added for thermal or optical properties? Broader functionality is described by calling each component in a composite a phase. Remember that the definition of a phase is a body which is chemically and structurally homogeneous, the same everywhere. This was first exemplified by metallic systems, but the same holds true when typifying composites. As covered in the first half of this lecture, a further structural description of composites are those that have constituents that are of different types, and these stay separate upon mixing, but the overall composite behaves as one, and the result is that which has different properties from each constituent. Describing composites as phases only changes the description of reinforcement. The matrix, that part which surrounds the reinforcement, remains unchanged. The matrix can be comprised of any of the engineering families or classes, metals, ceramics, or polymers. The role of the matrix also remains unchanged. It is responsible for physically communicating some external input to the reinforcing or dispersed phase, and further protects the reinforcement from these external inputs. The dispersed phase, depending on the form and arrangement, manifested as particle, fiber, or a structural inclusion, is what changes the behavior of the matrix. For ceramic matrix composites, any additional inclusion will aid in increasing toughness. For metal and polymer matrix composites, any addition of a dispersed phase will increase the operating temperature or resistance to thermal degradation. It is therefore not entirely correct to call the dispersed phase a reinforcement with mechanical connotations. Resistance to thermal degradation is a thermophysical property, not a mechanical property, and therefore calling the otherwise reinforcing phase a dispersed phase more broadly describes functionality. Let's now turn to how this may affect structural descriptions of composites. Well, not too much changes. We already know that dispersed particulate phases can be subcategorized on the basis of particle size, and at the opposite end of the spectrum, structural composites are unaffected by the shift in nomenclature. Fiber-reinforced composites, subtended by the description of the reinforcement form, is also unaffected. However, here is a point where we can further describe the forms that can be assumed by this class of composite. A continuously reinforced composite lacks dispersal and select orientations. The fibers are aligned along a singular dimension and can extend unbroken to the extents of the component in this dimension. Discontinuous fibers can also be aligned along a singular direction or randomly oriented. The degree to which the fibers can be randomly aligned is down to the overall domain and originating mixing technique. For a longer fiber length and a smaller width of domain, then the fibers will naturally align, detracting from being randomly oriented. Specific to fiber reinforcement, long continuous fibers demonstrate the highest degree of anisotropy. If the fibers are randomly oriented, and by virtue necessitating being shorter in order to fit, then anisotropy will be diminished. The fibers are less effective at establishing anisotropy on the basis of orientation. However, this is at the disbenefit of overall beneficial magnitude in any given direction. This is largely down to the effect of fiber length. Let's now examine why. If we look at a singular fiber in a composite reinforced by a long, continuous dispersed phase, then we have to consider the interface between the fiber and the matrix. For a composite which has a matrix which is less resilient than the reinforcing phase, pulling on the composite in the direction of the reinforcement will result in the matrix moving more than the dispersed phase. This therefore results in the interface between matrix and reinforcement being loaded in shear. What is being illustrated by the black lines in the central pane is the distribution of constant levels of this shear. If the fiber aspect ratio, that is, a measure of the length to diameter, is high, then there will be a significant uniform degree of shear between the matrix and reinforcement phases. At the ends of the fiber, there are non-uniform distributions of shear, but it is clear that the regions of uniform shear surrounding the fiber outweigh the end effects. Changing the aspect ratio of the fiber, the ratio of length to diameter, it can be seen that the overall length of the fiber engagement diminishes for a fiber with a larger diameter and a shorter length. This implies that a reinforcing dispersed phase with an equivalent volume to one which is longer and has a smaller diameter will have less fiber engagement. Another way, shorter, larger diameter fibers on a volumetric basis will be dominated by end effects rather than interfacial shear between fiber and matrix. There is a relatively simple formula which describes fiber efficiency on the basis of the length, strength, and diameter of the fiber and the strength of the interface between the fiber and the matrix. Whether or not a fiber will be effective is dependent on the strength of the fiber, the diameter of the fiber, and the strength of the interface between the fiber and matrix. This critical fiber size explains why a randomly oriented, short fiber reinforced composite will have properties being more uniformly distributed in any orientation. This means that it will be categorically more isotropic than a composite having a longer, more continuously reinforced matrix, albeit only in certain directions. This is because the overall interface relative to a loading direction can be significantly reduced, depending on the orientation of the fiber. If one were to change the aspect ratio between diameter and length to be approximately equal, then one would approach the properties afforded by a particulate reinforced composite. To unify the concepts of what a phase is and how it is to be employed within the context of earlier concepts covered in this course, it's necessary to neglect the definition of large length scale structural composites. Starting with a fiber-based composite, it's clear that as the fiber size diminishes, either by length or aspect ratio, then one ends up with a particulate reinforced composite. The matrix of a composite can be a metal, a ceramic, or a polymer, and this is unrelated to the relative arrangement of what can constitute a dispersed reinforcing phase. However, the underlying properties of each of these classes of materials can be employed to achieve remarkable properties beyond those which have been previously described. On the basis of matching properties between matrix and reinforcement, fiber efficiency can be decided on the basis of deformation rates attained in each matrix and dispersed phase. Further to this, if there are different thermal properties between the matrix and dispersed phases, what kind of behavior can be attained of the overall composite? What would happen to the overall composite if a martensitic transformation were to occur in the matrix of a, for example, metal matrix composite? This is an extension that leads back to the concept of mismatch and misfit residual stresses and how they can be harnessed to create very interesting properties. So in this part of the lecture, we've described composites in a broad sense, not on the basis inferred by the term reinforcement, but on the basis that all properties beyond mechanical ones can be changed by including a different material class or family. We've also described the breakdown of composites extending from being long, continuously reinforced materials back to particulate reinforcing ones on the basis of fiber efficiency. This description serves to explain why anisotropy is diminished for short, randomly oriented fiber-reinforced composite materials. Furthermore, a relationship between fiber and interfacial fiber and matrix strength, length, and diameter has been established on the basis of loading direction. All of these aspects are important moving forward to the next lecture, which will focus on the mechanical aspects of composite materials. Until next time.